Hello, welcome to Physics 100 level class. This is Kwara State University. I am Adegbenro Ajani. This afternoon we'll be teaching on work, energy and power. I'll be teaching on work, energy and power. Work, energy and power. So we look at work first. When you want to move a body, if this is a body, you want to move it with a force, then this is an angle through a distance to, this is point A to point B. You want to move the body here, then this is the distance, the displacement the body will cover. So when a force F moves its point of application through a distance x, work is said to be done. The work done by the force when its point of application undergoes a displacement is given by work, which is equal to F cos theta into brackets S, where S is the displacement. So work done is the algebraic scalar quantity which can either be positive or negative. So work is positive when we have positive work is in capital letter, when it is greater than 0. That is, if 0 is less than theta, and then theta is less than 180 degrees. So we have work as positive. Now, work is negative if work done is less than 0. Then at this point, it means 90 degrees is less than theta, and then theta is less than 180 degrees. So this is what we have here. So work done now is equal to Fs cos theta. So that's the formula for work done. And the force is always perpendicular to the displacement. The SI unit of work is Newton meter, because we are multiplying force, which is measured in Newton, and distance, which is measured in meter. And this is equal to joule. We call it joule. And it has the same unit as energy. I want us to look quickly at some problems, if possible 1 or 2, because of time. Let's see this problem. A body of mass 5 kilograms is drawn at a constant speed through a distance 6 meters along a horizontal floor by a rope exerting a constant force of magnitude 10 Newton at an angle of 30 degrees with the horizontal. Calculate the work done by the rope on the block. 2. The work done by friction on the block. 3. The total work done on the block. And 4. The coefficients of kinetic friction between the block and the floor. So let's see solution now. We want to drag this body through angle 30 degrees, and of course there is a normal reaction, and there's another force acting opposite there, and there's a frictional force acting there. So Roman figure 1 says we should calculate the work done by the rope on the block. So of course, work done is equal to F dot S, which is force times distance, and at this point we have Fs, because they are vectors, cos theta. So, and our theta is 30 degrees. So we're going to have our F, which is 10 Newton multiplied by distance 6 meters, then cos 30 degrees. So if you do this, it's going to be work now will be equal to 52 joules. 52 joules. So that's the first thing that we are asked to do. The second question says, it said, the work done by the friction on the block. So let's see the work done by the friction on the block. Roman figure 2 now. Work done by the friction is going to be F, the cross product of S. And of course, this is FRS. And this is equal to the frictional force multiplied by the distance cos 180, because we are dealing at a plane here. So it's going to be equal to 10 cos 30 degrees, because that's your F, your frictional force, then multiply by 6, then cos 180 degrees. So this is going to be minus 52. If you calculate that way, joule. That's what we have. Then Roman figure 3 says the total work done on the block. So let's calculate the total work done on the block. So it's going to be total work done, Roman figure 3 is going to be total work done. Let's call it W total, which is equal to work done by the tension. That's the first one. Tension minus, we will add it with the frictional force with the second one, which is the force done by the friction. So it's going to be 52 plus minus 52, everything in joules. Then of course it's going to be 0. So the answer is 0 for the total work done. Then the fourth question says, question number 4 says the coefficients of kinetic energy friction between the block and the floor. Okay, let me okay. All right, now remember that frictional force, the coefficient of friction, is equal to frictional force over normal reaction over n. And of course, we have our frictional force to be 10 cos 30 degrees divided by n. So we need to find n. What is n? Remember, n plus frictional force minus the force acting upward on the body is equal to 0. And of course, n now plus, we already have F cos 30, 10 cos 30, 10 cos 30 degree, which is our F, our frictional force, then minus M, which is 5, multiplied by, what is G? 9.8. Take your G to be 9.8. So N now here is equal to 49. If you do all this, you will have your N to be equal to 44 Newton. That's what we have as N. Having done that, and you come back to your reaction, coefficient of friction, which is equal to 10 cos 30 degrees divided by 44. And of course, this gives you 0.2. So that is the answer. Then we look at the energy now. What is energy? Quickly, what is energy now? And energy has two forms. We have when we deal with mechanical energy, it has two forms. Of course, energy is the ability or capacity to perform work. Energy. Let's see. Okay. Energy. So we said is the ability to perform work. Energy and work, they have the same unit. They are measured in the same unit called joule. Energy is measured in joule, and also work is measured in joule. So the forms of mechanical, of course, we have types of energy. If you can remember your O-level, electrical energy, solar energy, heat energy, chemical energy, and so on and so forth. Whatever that can cause, can determine the ability or capacity to perform work. So let's see the mechanical energy and the forms of mechanical energy. Mechanical energy, because we are dealing with mechanics now. So the forms of mechanical energy is potential energy and kinetic energy. Kinetic energy. So those are the two forms of mechanical energy. So what is potential energy? Potential energy is the energy a body possesses by the virtue of its position when it's at rest, while kinetic energy is the energy body has when the body is moving, when the body is in motion. And we need to understand that potential energy is also equal to work done, and when the body falls freely to the ground. So you can say that potential energy P sub E is equal to force times height. The force on the body when it moves, when it falls freely at a height h. So which is equal to, force is, because it falls, so we're dealing with gravity here, so it becomes mgh. And that's how we have that. So we're looking at kinetic energy now. So kinetic energy is the energy possessed by a body when it is in motion. And if a variable force causes a displacement from 0 to point x, if that body moves, the body moves from 0 to x, to point x, on the surface, then the work done is given as the W, which is equal to F, that's force times distance. Okay, that's the change in work is going, that's we are moving from 0 to x, is going to be force dx. Force dx. So with this work now, at this point, is going to be integral 0 to x f dx. And of course, this is equal to integral 0 to x and m dv dt dx now, because dv dt is the acceleration, because force is equal to mass times acceleration. And of course, this becomes integral 0 to x mv dv. So with this, when you integrate this, you will have kinetic energy to be equal to half mv squared. And that was how they arrive at the formula of kinetic energy to be equal to half mv squared. Now, if the body moves through two sets of velocity, it has initial velocity and it has final velocity. So it's going to be your kinetic energy is going to be m into bracket, you can say v minus u everything squared. So that's if there is a velocity change in the body. So let's look at work energy theorem. Work energy theorem. Work energy theorem states that states that the work done by the resultant external force acting on the body is equal to the change in the kinetic energy. So W is equal to, which is kinetic energy of 1 minus kinetic energy of 2, or let's say this is 0, or we'll say final and initial, so which is the change in kinetic energy. So it becomes change, that's the E. That's what work energy theorem says. It states that the work done by the resultant external force acting on the body is equal to the change in kinetic energy of the body. And let's see one or two examples there before we move on. This question says a proton is accelerated at 3.6 times 10 to the power 15 meter per second through distance of 3.5 centimeter. If the initial velocity is 2.4 exponential 7 meter per second, find the change in kinetic energy at the end of the distance. And we are given the mass of the proton to be equal to 1.07 times 10 to the power minus 27. So we are asked to find the change in kinetic energy, which is in form of the formula we have written up. So change in kinetic energy, solution now. Change in kinetic energy, delta K of E is going to be equal to half mv squared minus half mu squared. And then using v squared, which is equal to u squared plus 2as. So we want to get the value for v first because we know the u. So we want to get the value for our final velocity. Of course, this is equal to, if you put in the given values, you have 2.4 times 10 raised to the power 7 squared, that's your u squared, plus 2 times 9 points. Okay, you are given acceleration to be 3.6 meter per second squared times 10 raised to the power 15. Then multiply by, we convert 3.5 centimeters, we convert it to meters, so it's going to be 0.035 meters. So if you do this, you will have 3.28 times 10 raised to the power 14. So please try and do it yourself. That's meter per second. That's your V now. So if you have gotten V, the change in kinetic energy now will be equal to, which is already the kinetic energy 1 minus my kinetic energy 0, which is final minus initial. So it's going to be half. Substitute those values inside. Multiply by 1.6. That's the mass. 7 exponential 10 raised to the power 27 minus 27. Then into brackets 3.28. That's your velocity times 10 raised to the power 14 minus 5.76 times 10 raised to the power 14. Those are your velocities. So which is equal to 2.1 times 10 raised to the power 13, and the unit is joule. The unit is joule. So this is what we have, because half m is common to the two. Half m is common to the two. The only difference we have is their velocity, which is when you put the velocities inside. We've been given the first velocity to be equal to that. So when you put them inside, that's what you eventually have. So with this, I believe let's look for one more example. This one says, let's look for this. It says a body of 2 kilograms has its initial velocity of 8 meters per second in the x direction as it passes the origin of the coordinate. It is subject to a retarding force such that f of x is equal to 0.5. They said, what is the position, the coordinate, when it stops? That's what the question asks us to determine. What is the coordinate? So they're asking us what is our x as a matter of fact. So this is solution for that. From work energy theorem, don't forget that work done is equal to change in kinetic energy. That's what we have written. Then what is work done? Work done is force times distance. That's Fx. Force times distance, which is equal to half mv squared minus half mu squared. So which is going to be equal to f times x. They've given us that to be minus 0.5 x, which is going to be equal to 0 minus half mu squared. Mv squared is equal to 0, so it's going to be, because v is equal to 0, it's going to be half times m, which is 2 kg, times 8 squared. Then of course our x now, if you do this, x is going to be equal to 128 meters. So please try and play with that. From here, I want us to see the principle of conservation of energy. The principle of conservation of energy. Principle of conservation of energy. They said energy, any form of energy may be transformed from one form to another. For instance, mechanical to heat when rubbing against friction, heat to mechanical in heat engine, or mechanical to electrical energy at hydroelectric station. In any of these transformation, a principle always holds, and that principle says for a closed system, the total energy remains constant. So the principle of conservation of energy says for a closed system, the total energy remains constant. In a mechanical system, the principle of conservation of energy will imply that in the absence of any dissipate forces like friction, the total energy is always constant. So let's see this example for a free fall body. For example, when the body falls from a height, its potential energy is being conserved to the kinetic energy. You convert it, or it's being converted to kinetic energy such that the kinetic energy gain is equal to potential energy loss. So half mv squared is going to be equal to mgh, where your v is the velocity acquired, and of course at that point the g is going to be let's illustrate that. So the energy is converted, half mv squared is converted to mgh, so it's going to be equal. So from this, m cancels m, I believe, then v is going to be equal to square root of what? m2gh. That's what we have when you cross multiply. That's what we have left, where h is the falling height, the height by which the object falls. Let's illustrate this. Illustrate this with height h now. So if a body is dropped from a height h, if this is height and this is the floor, if we drop a body from this height, if a body is released at rest at that height, and we call this height h, if this height is h, above the floor, the total energy at this point of release, when we are releasing the body, the total energy is equal to the potential energy. So let's call it U, or we call it potential energy. So that's the total energy that takes place here. Now, also, when the body is about to hit the ground, just at this level, the body is about to hit the ground. So the energy here, the body will possess absolute kinetic energy. The body here possesses all the energy here is potential energy. At this point, kinetic energy is equal to 0 here. So at this point, potential energy is equal to 0, but kinetic energy is maximum. So what we have here is purely kinetic energy, which is half v squared at this point. Now, the point is now, what will now happen at the middle? When this body is at the middle here, when you release the body and the body gets to the middle, the principle of conservation of energy tells us that at this point, the potential energy is converted to kinetic energy. So at this point, potential energy is equal to the kinetic energy, because at this point, our height is equal to 2. This is half the height. So our height is equal to 2. So this body will have half kinetic energy, half, then half. Then potential energy also will be half. So at this point, to make up the total energy. So what we are saying is, at this point, if we had kinetic energy plus potential energy, it's going to give us the total energy. So that means as it falls, its potential energy decreases, but its kinetic energy increases to compensate, so that the sum of the two remains constant. The sum of the two still remains constant. Now let's calculate what happens at the middle there. So what happens to potential energy and the kinetic energy when the body falls to half? How do we go about this now? Let me get a fresh page. Now at that point, the distance here, you're going to have the potential energy 2, because 1 is when it is on, so which is going to be equal to mg, then h, but our h at that point is h over 2, is half h when the body is at the middle. Then kinetic energy 2 also at that point is going to be equal to half mv squared, squared. So the total energy at this position, E now, is given as half mv squared plus mg into bracket h over 2. That forms our E sub t, or total energy. So at this point, if we say the total energy at this position is given as that, then our U, our normal potential energy, which is equal to mgh, because potential energy is equal to kinetic energy, or total energy is equal to potential energy, which is equal to half mv squared, then plus mgh divided by 2. So with this, before the body hits the ground or strike the ground, its potential energy is 0, and its total mechanical energy at that point is just E, which is equal to half mv. So let's say v final now squared. So here now we're going to have total energy to be equal to mgh to be equal to half mv final squared. That's what we have at that point. And of course, the value of kinetic energy is equal to the original value of the potential. That means this value at this point is also equal to the original. Is also equal to the original value of the potential energy. It is now clear that as the body falls, its potential energy is converted to kinetic energy. Thus, a free falling body has potential energy, which is equal to kinetic and plus kinetic energy, plus kinetic energy, which is equal to constant For a free falling body, the potential energy plus kinetic energy is equal to constant. Let's see this by solving a simple, I believe, problem. This problem says a body uses a rope attached to the top of a ceiling to swing forth and back. The lowest and the highest point of the swing is 1.5 and 2.5 above the ground respectively. They said, what is the body's maximum speed? What is the maximum speed of the body? All right. At the highest point, this is what they are saying. You have the body attached to the ceiling, and then so there is a height. This is the ground. This is the body. There is a height on the that it has with the body. Then at an angle here, it has another height. So this is another height at this point. So it has two heights, and one is what are you given? One is 1.5 and one is 2.5. So this is 1.5. This one is 2.5. So at the highest point, the body has only potential energy because it's at rest. So at that point, potential energy is equal to mgh. At the lowest point, it has kinetic energy and potential energy. So when at the lowest point, it has the two energy, so it becomes half mv squared plus mgh. So at the lowest point, So at the lowest point, according to principle of conservation of energy, we said that potential energy, which is mgh, is equal to that's your total energy, is equal to half mv squared, the mv squared plus mgh. Your total energy is equal to kinetic energy plus total energy. This total energy, of course, which is also equal to potential energy. So at this point now, we have solving through all this. Of course, m goes in all. So you have gh is equal to v squared over 2, then plus gh. So at this point, v now, if we make v solid of the formula, or we say v squared is going to be 2g when this one move here. So it will be 2g into brackets h. That's what we have here. And our h is h0 and h1. The initial, this is equal to. So v squared now is going to be 2g into brackets h naught minus h, or we say h1 minus h0, as the case may be, depending on what you are using. So from this point, v now is equal to square root of 2g into bracket h1 minus h0, or h0 minus h1, depending on the one you are using. So the dimension you take. So at this point, we are given 2h. So v now is going to be equal to square root of, what are we given acceleration? So take g to be equal to 9.8. 2 multiplied by 9.8 into brackets 2.5. Those are your heights, minus 1.5. So this is what we have. Then your answer is equal to 4.4 meter per second. This is what we are asked to do at that point. So the next thing we'll look at is power. Power. Of course, power is work done in time taking, the time it takes to do a particular work. So it is the how work is being done, how quickly work is being done. That's what we call power, or we call it the time rate of work done, or the time rate of energy, or we say energy expanded per unit time. So that's what we call power. So power is equal to work done over time, or we say energy over time. Of course, work done is force times distance, FD over time taken. So we say time taken. Let's use small t to denote that. Okay. Now, when a quantity of a work is done during a time interval delta t, the average power is then asked to be defined. If there is work done at an interval of work done at an interval of time, so we're going to define what is called an average power. So average power is going to be equal to change in work done divided by change in time. So we also have what is called instantaneous power, and which is equal to the limit of time tends to 0, change in work over change in time. And of course, this is equal to dW dt when that is done. So the SI unit of power is joule per second, because we are dividing work done or energy by time, joule per second, and that's what we called or joule per second, or we call it watts. That's what we call watts. So 1 joule per second is equal to 1 watt. So a large unit of power is what we call horsepower. So big power now is, we measure it in horsepower, HP, horsepower, horsepower. And then 1 horsepower, 1 HP is equal to 746. Don't forget this, watts, 746 watts. And most of your pumping machine, if you can check them, they are measured in horsepower. So when the force acts on a moving body, the power developed can be expressed in terms of the force and velocity. So we can also express the power of a body in terms of the force acting on that body, and then the velocity. So, and this is what we do. Suppose a force F acts on the body while it undergoes a displacement delta S. This is force delta S. So if the frictional force is correspondent to that of F tangent to the path, then the work done is given by the W is going to be equal to F of T delta L. F of T delta L. So the average power now, P average, is going to be equal to change in W, which we have written before, over change in time, which is equal to Ft, that's divided by delta S, which is equal to delta change in time, delta T. And with this, this implies that power average is going to be equal to F T V. That's our velocity. That's our velocity average velocity. So in the limit, as delta t tends to 0, we obtain the instantaneous power. And at that time, the power, instantaneous power, becomes F of t v, where v is the magnitude of the instantaneous velocity. So let's also see one or two examples here before we go today. So example now. This question says, an airplane engine develops a total thrust of 10,000. An airplane engine develops a total thrust of 10,000 newtons when it is flying at 250 meters per second. Calculate the power developed by the engine in horsepower. So I think the major work there is just the issue of the horsepower. So with this, we are given F to be equal to 10,000 newton, and of course we are given velocity to be equal to 250 meters per second. So the major thing we are asked to do is to find the power developed. So P is equal to velocity, force times velocity, which is equal to 10,000 multiplied by 250 meters per second, which is equal to 2.5 times 10 raised to power 6 watts. That's 10 raised to power 6. I hope I'm correct with that. Watts. So with this point, at this point, we will have to take 2.5 to horsepower. So we have our answer in watts, so we take it to horsepower. Just divide by the horsepower. So power in horsepower is equal to 2.5 times 10 to the power 6 multiplied by 1 over 746. That's the horsepower. So which is equal to 3 point. Is it 3? So 3.351 horsepower. So try and find out if that is the correct thing. So just try and divide 2.5 times 10 to the power 6 divided by 746 and see what you will get at the end of the day. So that's what you have in horsepower. So let's look at the last example today before we call it a day. This one says a body of mass m, which is equal to 40 kilograms. Find a body whose mass is 40 kilograms. Find that it can run. A boy whose mass is 40 kilograms finds out that it can run up to a flight of 50 steps, each 15 centimeters high, in 5 seconds. So how much power is required? So the boy is climbing staircase. That's what the question is trying to tell us. So the boy is moving, at steps, and is moving at those steps. If solution, if this is the step, the boy is climbing. He climbs here, then he climbs here, then so we see the boy trying to climb those steps. Now, force that he used to overcome these steps was overcame is equal to height, which is equal to 40 times 10. That's the force that he used to make the climbing. So if our 10 is acceleration due to gravity, so the boy has the force of 400 newton. 400 newton. If the force he used to take up this height, because it's working against gravity. Now, distance covered is equal to 50 into bracket 15. 50 steps, then multiply by 15 centimeters. So we take centimeter to meters. That's why we have that, and which is equal to 7.5 meters. So first now is going to be, the work done now, work done is going to be work done is going to be force times distance, which is equal to 400 newtons multiplied by 7.5. So if you do that multiplication well, so your work done is going to be equal to whatever you have, 400 times 7.5. So then your power now is going to be equal to work done over time taken, which is going to be equal to your work done times 7.5 divided by what is the time? We are given 5. So the answer is, when you do that very well, you should be able to have 600 watts as the answer. Ladies and gentlemen, this is where we call it a day. Someone else will take you next week by the grace of God, but you'll be given 1 or 2 assignments again to be submitted on Monday, just like you did this Monday. I've seen all the assignments submitted, and they shall be attended to accordingly. Till next time we come your way. Bye for now. Kindly get your questions ready on Thursday and Friday, so that we can attend to as many questions as you have. Thank you and goodbye.